Hello, my name is Nathan Dunnigan, and this is my Lab 4 Oscillations for Physics 1. For the introduction, I will be talking about the purpose of the lab, which was to demonstrate and predict the motion of an oscillating object using the law of energy conservation and Newton's second law to predict the changing velocity and updating position. The preview of the lab is to use the tracker analysis of a mass on a spring to demonstrate the oscillating object and to analyze the graph of the oscillating object, as well as comparing and contrasting the actual model versus the computational model. The system is the earth mass and spring while the surroundings are none, and it is important to note that the change in energy is equal to zero. The first fundamental principle is Newton's second law, which is the momentum principle, which states that net force is equal to the change of momentum over time, and we will also be using velocity update formula, which allows us to predict the final velocity of the system during a specified time interval, and the position update formula, which allows us to predict the final position of a system at a future time. The next fundamental principle is net force, and in this case we will be looking at the gravitational force and the spring force, and then net force will be the sum of these two forces. And there's a little diagram on the left to just show a pretty easy understanding of this. Another fundamental principle we will be using is the energy principle, which states that a change of energy in a system is equal to the work done by the surroundings plus the exchange of thermal energy between the system and surroundings. The total energy is equal to the sum of all energy transfers. In this experiment, we will be focusing on the translational kinetic energy, spring potential energy, and the gravitational potential energy, where the three equations are below, and I will show you how these equations are used in our computational model later on. The brief model description and preview shows that we will illustrate comparisons between the predicted model and the observed motion of the mass, and we will plot the energy changes that we compute in the model. And we expect similarities due to the use of data from the observational model, but differences in the expected data could be for not accounting for other energies. Here is my tracker analysis, which is a real-world demonstration of the laws of motion. And as you can see to the left, it provides this observational data to be used in the computational model. The initial conditions of the ball, or the mass, is that the mass is 0.402, the position and the velocity are also below. Here's the computational model initial conditions. We have the mass, position, and velocity, which was talked about earlier. We have the gravitational constant, which is equal to 9.8, the spring stiffness and relaxed length of the spring, and I explained how I got vector L by using the ball position and L0 to calculate it. And then, like I talked about earlier, we see the three energy formulas. And here's my calculation loop for the computational model. First, we calculate the net force using the gravitational force and spring force. Then we will apply Newton's second law to update the velocity and position. Then we update the position of spring with new variables used earlier, and then we recalculate the energies and subtract the initial energy from the new energy to find the change in energy, just using those energy formulas I talked about previously. And here is my model, which shows that the total change in energy remains constant at zero, and that energy is transferred between kinetic, potential, gravitational, and potential spring energy. The blue is the change in kinetic energy, red is change in potential gravitational, green is change in spring potential, and the orange is the change in total energy. After running the code, the three graphs to the right were created, illustrating the energy changes, the change in the x position of the mass, and the change in the y position of the mass, comparing the model versus the experimental data. The change in energy graph shows the shift in energies between translational kinetic energy, potential gravitational energy, and potential spring energy. The x position versus time graph shows the computational model trajectory in blue versus the experimental data in red, and the y position versus time graph shows the same thing but in the y direction. Both are very accurate, but there are also some differences that will be discussed later on. Some possible sources of error are that we did not account for all forces such as drag, we did not account for thermal or rotational kinetic energy, and there could also be a possible user error of inconsistent marking and tracking. However, there are some similarities and differences, such as the graphs being very accurate comparing the experimental and the observed model, and all of the models accounted for gravity and the force of the spring, but the differences could be due to possible sources of error talked about earlier. For the first what does it mean question, we will be answering if our model satisfies the energy principle, and the answer is yes, which is shown in the graph to the right in the change in energy versus time graph. The total energy is zero because the spring potential energy has an opposite sign to the gravitational potential energy, and the kinetic energy has the same sign as the potential energy with less magnitude. We can see that the change in total energy is equal to zero, as it is the orange line in the graph. And for the final Discussion question. We will be talking about the period of oscillation, which is the time period between two crests or two troughs. The average oscillation period can be calculated by finding the average of the 3 cycles, which is seen to the picture to the right. For the X position, the average oscillation period is 1.677 seconds, and for the Y position, it is 1.55 seconds, which makes a difference of 0.127 seconds. The difference between the two oscillating periods can impact the calculation of spring constant K, the spring force, and the spring potential energy, and these differences may be caused by drag forces or incorrect tracking of